we will now detail the splitting criterion used to select the split in each node of the tree. To do this, we first define an impurity criterion to measure the variability of the output variable within a cell. This criterion will be denoted imp-A, which stands for the impurity in a cell A. Several impurity criteria can be used to select the split to be performed. Formally, a split is defined by a couple Js, where J corresponds to the index of the variable along which the split is made between 1 and D, and S corresponds to the position of the split according to the given variable. To measure the quality of a split, we define the impurity reduction associated with the split as the impurity of the initial cell minus the impurity of the left cell, weighted by the proportion of points in the left cell, minus the impurity of the right cell, weighted by the proportion of points falling in the right cell. This quantity measures the reduction in impurity between the initial cell and the two cells generated by the split considered. Intuitively, if the split is not informative for predicting the output variable, the impurity in the initial cell and the impurities in the two generated cells should be similar. This would lead to an impurity reduction close to 0. Conversely, if the split we consider corresponds to a large impurity reduction, the split results in cells with impurity much lower than the initial impurity. The value of the output is more homogeneous in the newly created cells. The learning problem has been simplified. Note that this impurity reduction is always positive and always lower than the impurity of the initial cell. Let's take an example. Let us consider the impurity reduction associated with the split J equal 1 and S equal 0.5. We therefore consider the split at position 0.5 along the first direction. To calculate this impurity reduction, let's first calculate the impurity in the initial cell. We then subtract from this impurity the impurity in the left cell, weighted by the proportion of points in the left cell, and we also subtract the impurity in the right cell, weighted by the proportion of points in the right cell. This is a calculation of the impurity reduction for the split J equal 1 and S equal 0.5. This calculation can be done for all splits, i.e. according to all possible directions and according to all possible positions along these directions. We then choose the split that maximizes this impurity reduction. Intuitively, we choose the split that leads to the most homogeneous cells possible in terms of output values. A measure of impurity quite classically used in regression is the empirical variance of the yi in the considered cell. The variance of the yi is a measure of homogeneity or impurity of the cell considered. The higher the variance, the more the yi's are dispersed around their mean. With this measure, we try to create cells in which the variance of y is as low as possible. We thus obtain a prediction, an average, in the leaves of the tree, close enough to the set of values in this leaf. The quadratic risk of the tree computed on the training set is then low. Let's go back to the procedure for selecting the best split. Let's go back to our example. As mentioned, we need to evaluate the impurity reduction of all possible splits according to each variable and at each position. A priori, we should compare an infinite number of splits. However, given a variable and two consecutive observations, any split between these two observations produces the same partition of the data and thus leads to the same impurity reduction. Therefore, we do not need to evaluate the impurity reduction for an infinite number of splits. We can just evaluate the impurity reduction for all the splits located in the middle of two consecutive observations. This choice of the middle is totally arbitrary. Other choices would lead to the same performances on the training set, but potentially to different performances on the test set. In concrete terms, we will calculate the decrease in impurity for all possible splits according to the first variable. Notice that by construction, each split is located in the middle of two consecutive observations. Once the impurity reduction has been calculated for each of these splits, we can consider the splits according to the second variable and calculate their impurity reduction. We thus obtain the impurity reductions associated with each split. We can thus choose the split that maximizes the impurity reduction. This is the split presented during the construction of the tree. This process is then repeated in each of the resulting cells. Remember that the split is optimized according to all possible variables. We want to find the best split among all possible splits, i.e. the best couple, split direction, split position.